Hello students, today we'll start the chapter, in chemistry we'll start the chapter structure of an atom. Structure of an atom. Important topic, very important topic, listen properly, okay? So, everything, first point of this, you can write, everything is made up of atoms. It's made up of atoms. Everything, maybe it's a living thing or non-living thing. Okay, they are made up of atoms. Now what are the example for this? Okay, first example you can write sugar, then salt, okay, sugar, salt, water, plants, animals, and even human beings. Okay, these are all made up of atoms. Yeah, maybe it is a living thing or non-living thing, but they are made up of atoms. Now, what makes the atom now? Okay, these all the things are made up of atoms here, but what is present inside the atom, that we'll do now. A small question. Okay, what makes the atom? What makes the atoms? Clear? Now what is the answer for this? What makes the atoms here now? Clear? What makes the atom here now? Three tiny particles. Okay, three tiny particles makes the atom here. What are the three tiny particles here? The first one is protons. The second one is the electrons, and the third is the neutrons. Clear? These are the tiny particles, very tiny particles. Okay, this all present in atom. Clear? Fine particles, very fine particles. Further we can't divide at all here. Protons, electrons, neutrons, we can't divide further. Okay, so these are present in atoms. Clear? Atom, we are all sugar, salt, water, plants are made up of atoms, and atom is made up of this proton, electrons, and neutrons. Clear? And the next one you can write their shapes. Okay, how they'll be the shapes. Okay, so their shapes like spiracles, spherical in shape, like ball. Okay, like ball, football. Okay, and their structures of all atoms. Okay, almost all atoms are same. The structure will be same. Clear? And inside the atom now, okay, the main very important one here, that is the center. Okay, the center dense particle. Okay, dense particle present in atom, in an atoms are called, what are they called? Nucleus. They called as nucleus. Clear? Now, small question here we can ask here. What is the question here? Why electrons revolve around the nucleus? Okay, here also one question we can ask, that why electrons revolve around the nucleus. Why they revolve around the nucleus? Just like planets, sun and the planets. Planet is also revolving around the sun here. Okay, they are not coming and colliding with sun here, but they are revolving here. What is the reason behind this? Clear. The reason is that the protons, okay, and the electrons, have some power in them. Okay, a force will be there in between them. Okay, protons and neutrons. Protons are present inside the nucleus, and electrons are present outside the nucleus. Both have the force, a type of force present in them, and that force is called electrostatic force. Electrostatic force. Because of this force what happens, the electron continuously revolving around the protons, that means nucleus. Clear. Same like if you take the magnet, I think already you know the properties of magnet. Like poles repel each other and like poles attract each other. Okay, if the south and south, okay, like poles are here, both repel each other. Clear. South pole and south pole, they repel each other. But if it is south and north here, they attract each other. Clear. So this electron have the south pole. Imagine south pole. Proton also have the south pole. So they repel each other. So due to that, the both are revolving. Okay, they are not attaching here. Clear. So that force is called as electrostatic force. Clear. And both the electrons. Okay, suppose if this is the orbital space, and one electron will be in this way, and second electron will be different way, clockwise, anti-clockwise. Okay, one electron are moving in a clockwise. Okay, second electrons move in the anti-clockwise. Clear. This is the movement. Okay, this is the movement of electrons here. Clear. The next theory tells about the quantum numbers. Quantum numbers. What is this quantum numbers means? Clear. So these are the set of numbers. Okay, the set of numbers used to describe the position and energy. Describe the position and energy. Position and energy of the electrons in an atom. Clear. This is a quantum number. Okay, this is the definition of quantum number. What are the definition of the set of numbers used to describe the position and energy, where the electron is present, how many energy present in them, that defines the quantum number. Clear. In that, again, the first point you can write quantum number, mechanical model of atom. Clear. This was explained by, briefly explained by Erwin. What is his name? Erwin Schrödinger. Erwin Schrödinger. This is a scientist name. Clear. This Erwin have explained about the quantum numbers. Briefly he explained about the quantum number. Then according to his theory, the second point, according to his theory, what he told, accurately we can't locate the position of electrons. Clear. And next he told that we can't predict also. We can't predict. We can't predict the region. We can't predict the region where the possibilities, you can tell, where the possibilities of finding electron. Is maximum is maximum that region, that all this region is called orbital, or that region is called orbital. This space will be very near to the nucleus, okay, where the electrons are moving. That space will be very close to the nucleus, and that is called as the orbital here. Clear? And these electrons, next one you can tell, an electron denoted by like this E, and charge negative. Clear? Electron will be always negative charge particle. Protons will be positive. Clear? Electron always negative and proton always positive. Clear? So an electron revolve, okay, electron revolve in a fixed path. Clear? Track you can tell, okay, and that fixed path is known as orbit. Clear? The fixed path is known as the orbit. Clear? And now I'll show you this one. See the diagram. Clear? This is the nucleus. Okay, near to the nucleus, these are the orbits. Red color circle, black color circle, green color circles, and brown color circle. They are the orbits. Okay, they are close to the nucleus. Okay, in these orbits only the electrons revolve. Okay, imagine solar system is the sun, and here are the planets. Okay, same like solar system, isn't it? All the planets are revolving around the sun. Same like that here also, all the electrons revolving around the nucleus. Inside the nucleus, neutron will be there, proton will be there, and then outside is called the orbits. Orbit 1, orbit 2, orbit 3, orbit 4, orbit 5, like that. Clear? These are the orbits. Okay, inside the orbit the electrons are revolving. Clear? And this was explained by, this structure of atoms was explained by many scientists, but out of many scientists, few are the very explained briefly, like Alfred Landé is there, Neil Bohr is there, okay, and Arnold Sommerfeld is there, J.J. Thomson is there, Uhlenbeck, Goudsmit is there. These are the scientists who explained briefly about the structure of an atom. Clear? These are the quantum numbers, 4 quantum numbers. Clear? These are the 4 quantum numbers, 1, 2, 3, 4. The first quantum number called as principal quantum number. This was briefly explained by Bose, okay, in 1922. Okay, in the year 1922, he explained about principal quantum number, and this principal quantum number denoted by n, small letter n. The next quantum number is angular momentum quantum number. This was explained by Sommerfeld, another scientist. Okay, Sommerfeld in 1915 to 1916. This year, what happened? He explained this one. And this angular momentum quantum number denoted by small letter L. Right. The next one is magnetic quantum number. This magnetic quantum number discovered by or explained briefly by Alfred Landé in 1921. Okay, he explained about this one, magnetic quantum number, and it is denoted by small letter m. Next one, the final one, spin quantum number. Okay, spin quantum number explained briefly by Uhlenbeck and Goudsmit. Okay, and this was denoted by S. Spin quantum number, just now I told you spin. Okay, spin of electrons here, anti-clockwise directions. Okay, these are the spin. This was explained by the Uhlenbeck and Goudsmit. Clear? Opposite direction, both clockwise and anti-clockwise. Clear? Now, next one is that what this principal quantum number defines. It defines this one. Okay, it defines orbit size and orbit energy. Orbit size. See the size of this first orbit here. N1 means orbit. N is what here? Principal quantum number. Just now I told you. Principal quantum number denoted by N. So this is N. First N, second N, third N, fourth N. Clear? So this is the first N. So this is the size of the orbit. Orbit size. See the orbit size. First one, small size. Okay. Check the next one. N2, little bit big. 3 still big. 4 still big. So size, okay, orbit size and orbit energy. Orbit energy, see the first orbit 1s, only one subshell is there in this. Okay, second you see the orbit 2 are there, s and p also are there. Energy level increases here. See the third one, s, p, d still increases here now. See the fourth one, s, p, d, f, Clear? So this is called orbit energy. In an orbit, how much energy is present and what is the size of the orbit, that is explained by principal quantum number, and it was explained briefly and good explained by the books. Okay, in 1922. Next, angular momentum quantum number. What it defines, subshells and shape. What is subshell? This is the shell. Red color one, N1. This is N2. This is N3, N4. These are only called shells. And what is the shell name? K, L, M, N. These are the shell names. Inside this shell, subshells are there. K shell. This is the K shell. Inside the K shell, S subshell is there. Understood? K in the K shell. Okay, one subshell is there. One subshell. See the L, L subshell. L shell is there. Only L shell. Inside the L shell, then L shell. How many subshells are there? Two are there. S and P. Two subshells are there. Check the next one. M shell. This is the M shell. See the M shell. Three subshells are there. S, P, D. Three subshells. Now see the N1. Last and most is here. Bigger one. It consists of how many subshells? S, P, D, F. Clear? This was explained by angular momentum quantum number. Clear? And to tell about these subshells, okay, one small formula is there. L equal to 0 to N minus 1. Clear? There is a formula. I'll show this one later. And next is magnetic quantum number. What it defines, orientation. That means orientation of orbitals, where actually the orbitals are present. Introduce of orbitals, depends on L. What is L here? Angular momentum quantum number. Magnetic quantum number purely depend upon angular momentum quantum number. Okay, orbitals. Orbital means space. In each orbit, how many orbitals are there? Okay, they are totally linked to this one, angular momentum quantum number. So finally, spin quantum number. Spin quantum number, I told you. Spinning here, see, clockwise and anti-clockwise. Clear? Electrons always move clockwise and anti-clockwise. And each orbital, this red colored box is called as the space. Otherwise, this space itself called as the orbital. Clear? The name of space is nothing but orbital. And where this orbital is present? Very near to the nucleus. See, they are very near to the nucleus. Clear? So these are the four quantum numbers. Clear? Next one. The next one. Okay. Next one I'll tell you shapes of the quantum numbers. Okay. Shape of the orbitals I'll show you. Okay, this orbital. Clear? Shapes of the orbitals. Shape of the orbitals. Okay, what are the orbitals here? SPDF. Just now I told you SPDF now. First you tell what is orbital means. Okay, orbital means what? Clear? So the space around the nucleus, the space around the nucleus, where there is highly possibilities of finding electrons, and it is known as or called orbital. Clear? This is orbital, and this orbital will be very close to nucleus. Clear? That you have to remember. Now shape of s orbital I'll show you. Shape of s orbital. Clear? S orbital. Clear? What the shape of s orbital? It is sphere in shape. Sphere means ball-like structure. Football. Okay, just like ball, it looks like a ball. So this s orbital consists of how many electrons? Suppose this is the s orbital. Okay, this room. Okay, orbital means space. Okay, in this space, two orbitals will be there, clockwise one, anti-clockwise one. Two orbitals will be there. Now that we have to show. Clear how it is present. Now, okay, draw the lines here. One is y-axis and x-axis. Clear? Show the figure. It is in circular here. Okay, this 1s1, 1s2 you can tell, 1s2. 2 electrons are there, 1s2. This is the first one. Okay, second one now. So 2s2. Okay, this is the second one. Okay, y-axis and x-axis. This is a little bit bigger than the first one. Clear? Because the second level 2s2, so it is different. First level 1s2, 2s2, both are different. Okay, both are different. Energy level will be different here. So the size of energy also will be different. Then the third one, y-axis and x-axis. Now here is still it will be bigger. So this is 3s2. This 1s2, 2s2, 3s2, it proves that s22 means what? Only 2 electrons are present in s orbital. Clear? In s orbital only 2 electrons will be there, not more than 2. Clear? 2 is a fixed one. Once the 2 electrons comes here, the room will be locked. Clear? This is the shape of a s orbitals. Clear? Now the shape of the p orbitals. Shape of p orbital. Shape of p orbital. Clear? For the shape of p orbital, it look like a dumbbell shape. It look like a dumbbell shape. We'll do exercise with the dumbbells, isn't it? Here, dumbbells. You can tell it is a dumbbells. The shape of this p. Clear? But in p orbital, still 3 spaces will be there in p orbital. That is called degenerate orbitals. Okay, degenerate orbitals. Total 6 electrons will be there in this. 2, 3, 4, 5, 6. So total number of electrons are 6. Okay, here names are given to it. This is a p orbital. Clear? This is a p orbital. Clear? X, Y, Z. Clear? Now we can show the shapes of this one. Clear? First shape. Clear? First p orbital shape. First shape about the x. Clear? Px square. Okay, 2px. Okay, then 2px2. 2px2 x. Where is the electrons are revolving here now? On x. So we keep y and x. So where it is revolving here now? X. So show the electrons revolving here now. It is revolving here like this. This is the shape, the first one, dumbbell shape. Clear? 2px2. Okay, the first one, x. Clear? P orbital, the electrons are revolving like this. Okay, on x. On the first one, x. 2 electrons, 1 and 2. 2 electrons are moving like this. Clear? The next one. The next one. Y-axis, x-axis now. Now it is a x is over. Now the y. Okay, 2py. Clear? This is 2px, this is 2py. 2 electrons will be there, always 2 electrons. So y here, here you show it. Like these electrons moving like this. On y-axis. Clear? 2p, on the y you have to show here. Here also 2 electrons. Here also 2 electrons. Here where they are moving here now? Along the x-axis. Here the y-axis. Now the third one. Check the third one now. Okay, y-axis, x-axis. Now the z is there here. Separate here. This is the z. Clear? Now the electrons are moving like this, in this way. Clear? 2 electrons, 1 and 2. Clear? This is called 2pz. Okay, always 2 electrons. So these are the shapes of the p orbitals and s orbitals. These are the shape, dumbbell shape. This one is the sphere shape. Clear? Next one. Next one about the p orbital. sp is over. Now I'll show you d orbital. Shape of d orbital. Shape of d orbital. d orbital. Clear? What is the shape of d orbital? It looks like double dumbbell. Okay, double dumbbell shape. Okay, like this, double dumbbell shape. Here one dumbbell and here one dumbbell. Okay, double dumbbell shape. Okay, then the d one now. Okay, shape of d in d orbital. Okay, how many orbitals will be there in d? Total spaces in d orbital is 5. 1, 2, 3, 4, 5. So how many electrons will be there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Clear? This many electrons are present here. Clear? In d orbital. Clear? In double dumbbell shape. Clear? In double dumbbell is a large big diagram is there, double dumbbell shape here. Then the fifth one, the last one is the shape of, this is the fourth one, and the fifth is shape of f orbital. Shape of f orbital. Shape of f orbital. This shape of f orbital is called as tetrahedral. Tetrahedral shape. And tetrahedral shape means, you know, the example like methane example here. Methane example is a good example for this. Methane formula is CH4. So for carbon, single molecule of carbon here now, how many hydrogen are attached here now? 4 hydrogen. Clear? 4. This shape is called tetrahedral. Tetrahedral means 4. Tetrahedral means here 4. Now see the shape here. This shape is called a tetrahedral shape. Clear? And how many spaces, orbitals will be there in F? How many will be there here? Total 7 will be there. 1, 2, 3, 4, 5, 6, 7. Okay. 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. Total 14 capacity. 14 electrons you can find here. Okay, this many electrons can accommodate in this. Clear? This is the shape of the f orbital. Clear? Clear? Spin content number already I told you what is the spin content means here. Okay, clockwise and anti-clockwise. For this, spin content number denoted by S. Already we studied about that one, you know, and it is indicated by plus of, minus of. Clear? Next one we'll do some important points over the theory. Okay, what are the important points? You know, is prove that some important points of this theory. Okay. What are the important point? You know, the first point is that a single shell. Listen carefully. A single shell or orbit can accommodate how many electrons? This we have to show. How many electrons? Okay. For this one, formula is there. Okay, what is the formula? Formula is 2n square. This is the formula. Clear? Each shell or each orbit, how many electrons can accommodate? How many electrons can come? Just now we are showing here now. This many electrons are there in this orbit, F orbit. Clear? It's the F1. Clear? Now like that we have to show here. So first one, n equal to 1. Okay, what is n means here? Principal quantum number. Okay, already told you principal quantum number. What is n means here? No, principal quantum number. This one. See, this n1, n2, n3, n4. So the n1, we are talking about n1 now. In n1, check it out now. So formula you do it here. n1 is equal to, what is the formula? 2n square. Take it 2n square. So for that, this is the first one, isn't it here? So write 2, instead of n you write the 1. 2 into 1 square. So how many electrons can accommodate in this here now? 2 electrons. 2 electrons, right? Clear here? Here 1 1. Sorry, 1. Because n value is 1. So instead of n we have to keep the 1 here. Clear? 1 into 1, 1. 2 ones are 2. 2 electrons. Clear? Next one. Suppose if the n value is 2, then what is the formula here now? Same thing. 2n square. Now here 2 into, what is the value here? 2. 2 square. Now how many you will get? 2 to the 4. 4 to the 8. 8 electrons. 8 electrons. 8 electrons can accommodate in second orbit. Clear? Now the third one, quantum number 3. Okay, same formula you write it here now. 2n square. Then 2 into 3 are 3 square. So how much you are getting? 3 3 is 9. 9 2 is 18. 18 electrons. 18 electrons can accommodate here. 18 electrons here. Now n equal to 4. Fourth orbit now. Clear? Same formula, 2n square. Okay, now 2 into 4 is here. 4 square. 4 4 is 16. 16 2 is 30. 32. Clear? 32. 32 electrons can accommodate here. Clear? Like this we can take out. Okay, this is a small formula, 2n square. With this we can know that how many electrons will be there in first orbit, second orbit, third orbit and fourth orbit. Clear? So these are the subshells now. SPDS is the subshells. In subshells, how many electrons are accommodated? Clear? These are the orbit. Inside the orbit, what is this n here called? Here you can give the number n. It is first one is called as the K. Okay, K shell. Here KL. This M. This is N. These are the shell. These are the subshells. S, P, D, F. These are the subshells. What are they called as here? Subshells. Clear? Now the next one. Total second one you can explain here now. Number of electrons. Number of electrons can accommodate in a subshell. Okay, in a subshell formula. For this also one formula is there. Now what is the formula? 2 into 2L plus 1. This is the formula. 2 into 2L plus 1. This is the formula here. That's with the same thing we'll do now. Subshells we have to show here. What the shell means here now? Just now I shown the diagram. What is the shell and subshell? Clear? In the diagram, what the shell means here? These are the shells. K, L, M, N. These are the shells. Red color one, black color strip, and green color, brown color. They are the shells. K, L, M, N. What are the subshells here now? In K shell, S. S is written here now. That is a subshell. In L, SP is written. They are the subshells. In M, SPD is written. They are the subshells. In N, SPDF written. They are the subshells. Clear? Now check it out here now. S, P, D, F. Okay, S, P, D, F. These are the subshells. Clear? What are the shells here now? K, L, M, N. Clear? These are the shells. These are the subshells. Clear? So S subshell. In S subshell. Now for apply the formula again. This is the formula, clear? 2 into 2L plus 1. This is the formula, clear? Now on the S, how many are there? 2 are there. 2 electrons can accommodate in there. So 2 into 2. 2 into the first one is 0, isn't it? Here SPD value is what? 0. 2 into 0. 0 plus 1. So how much you are getting here now? 2. 2 into 0 is 2 only. So 2 electrons can accommodate here now. 2 electrons can accommodate. 2 electrons can accommodate. See the next one, P subshell, you know. P subshell. Same formula, you write it 2 into 2L plus 1. Okay, L value is 0 here now. So like that. Now here 2 into, okay, not a bracket here. 2 into 2 into L here 1 isn't it? 1 plus 1. So how much you are getting here now? 2, 3, 6 you will get here. Clear? 6 electrons. 6 electrons can accommodate here. Now the d orbital here, subshell 2 into 2L plus 1. Clear? Then here 2 into 2 plus 1. How much you are getting here now? Okay, 10 electrons can accommodate here. Can accommodate it here. Clear? And the last one is the F subshell 2 into 2L plus 1 gives. Next one last is 2 into 3 plus 1. So how much you are getting here now? 14 you are getting here. If you multiply you will get, okay, 14 electron can accommodate. Clear? These are the number of electrons can accommodate in subshells. In each subshells you can find this all data. These are the electrons, S, P, D, F. Clear? 2 electrons, for that we can show the orbital shapes also here. Okay, suppose if it is a S subshell, first one, F subshell here, this S is the subshell here, first one, K is the shell. Clear? K is the shell. In that K shell, this is S is the subshell. So in this, if you want to show the orbital here, no, show the box like this. Clear? How many electrons can accommodate in this here? 2. So 2 electrons you can show clockwise, anti-clockwise. Clear? Now the second shell here, K, L. Clear? L is there. In L, P. Subshell is P. Clear? Then in P, how many orbitals are there? You know, degenerate orbitals are there in P, isn't it? So 3 subshells are there in this. Okay, P degenerate shells will be there here. Orbitals are there here. In this, how many? 2, 3, 4, 5, 6. Clear? Here total how many? 2. Here total how many? 6. Clear? 6. Check the next one. KL M. M shell. Okay, then what are the D and subshell? Now in D, how many here now? 5 degenerate orbitals will be there. 5. How many? 5. 1, 2, 3, 4, 5. Clear? So here how many electrons can accommodate? In each shell, in each orbital, only 2 electrons only will be there, not more than that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total number is 10. Clear? 10. With the formula, with this formula we are doing same thing here. Clear? Now next one is the N. See the N shell. N shell, what is subshell here? No, F. Okay. Now F how many here? No. Total number of degenerate orbitals are 7. How many? 7 are there here. 1, 2, 3, 4, 5, 6, 7. Clear? Now in this, see how many electrons will be there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14. Clear? This the boxes shows the orbitals. Orbital is nothing but a space, and space will be very near to the nucleus. Clear? Now after this, I'll show you Hund's rule. If you know the Hund's rule clearly, then you can do the electron configuration. Very important topic now. Electron configuration. How to do the electron configuration with elements, different elements here. For that, you should know what is Hund's rule means. What is Hund's rule? Hund's rule. Clear? What the Hund's rule tells here now? Pairing of electrons. Pairing of electrons. Pairing of electron take place. Takes only after filling up of all degenerate orbitals with one electron each. Clear? Suppose oxygen will take the example now here. Okay, example, oxygen element is oxygen. Okay, what is the atomic number of oxygen? Atomic number of oxygen is 8. Clear? Oxygen is an element oxygen, you can write here, element oxygen. So atomic number of oxygen is 8. Now you draw it here now. Box, remember the box compulsory. Okay, first you write 1s, then 2s, then 2p. Clear? Don't write 1s2, 2s2, nothing. Just write 1s, 2s, 2p. Now draw the boxes here. 1s here, then 2s, then 2p. In 2p, degenerate orbitals are there. 3 are there. 1, 2, 3. Clear? Like that we have to show. P always have the 3, x, y, z. This is the x, this is the y, this is the z. Clear? X, y, z. Now fill the electrons here. Total number of atomic number is 8. 8 we have to fill, we have to show here. So 1, 2. This orbit is completed now. This s orbital is completed, fixed. Once the 2 electron comes here, it will be locked. There will be no any chance to get other electron here. Finished. Capacity of s orbital is to take only 2 electrons. Here also s is there. So 1, 2. 1, 2, 3, 4. 4 are there. Now we have to get 8 here now. Now here see 1, 2, 3 are there. Each, once again this orbital consists 2 orbitals here now. So you take 1, okay, 2, okay, 3. Clear? 4, 5, 6, 7. Still 1 is there. Clear? That one you can take here. 8. You can take here, you can take here, you can take here. Anywhere you can take it. Because all the orbital shells consist of same energy. Same level of energy. So you can write here or you can write here. But count now. 2 here, 3, 4, 5, 6, 7, 8. Now you write it. How many electrons are here? 2 are there. So 1 is 2. How many electrons are here? 2, 1, 2. 2 is 2. How many electrons are here? 1, 2, 3, 4. 2p, 4. So what is the electronic configuration of oxygen? Nothing but, how do you write here now? 1 is 2, 2 is 2, 2p, 4. This is the answer here. Okay. So what is the actually Hund's rule tells here? What are the Hund's rule tells? 2 important things it will tell here. Okay. The first one is that every orbital in a subshell, singly filled with one orbital before before any orbital doubly filled. Okay, doubly filled. Clear? First you fill this two, then only you have to go to the next one. That's the meaning of this sentence. Clear? First fill the s orbital. S orbital is very near to nucleus, so first we'll be filling with the s. The next very close is s, 2s once again. Then after that little bit for p, but p have the three degenerate orbitals, 1 2 3. Each orbital, each space, again you can fill 2 electrons. So total number of p degenerate orbital consists of how many? 6 are there here. Clear? So according to the element atomic number, you have to fill the electrons. The first one, first rule here. Okay. Second, you can tell, second point, all electrons in singly filled, all singly filled orbitals have the same spin, Clear? Now have the same, all electrons in the singly filled orbital have the same spin. That means see, singly upward, same thing here. But secondly, when you're feeling, it should be opposite. First you are filling the electron like this here, or you can show like this way, or you can show this one also. But suppose if you are showing like this way, then the second one will be like this. Or first one, if you are showing like this here now, the second one will be like this. Clear? This is the second point here. Clear? Now from here, the next one I'll show you the electronic configuration of few elements. So first 3 or 4, 5 I'll show you. Remaining what happened here, you can do. Okay, remaining you can do. Remaining you have to do with me, along with me, then easily you can get the electronic configuration. Many of the students will think that electronic configuration is very tough, very hard here, but it is very easy here. Okay. Very easy. I'll show you that how to fill these all things here. See, this is the structure of element, all the atom here now, and here this is the way. This is an easy way. If you remember this one, 1s, 2s, this whole thing, it's a very easy to fill the electrons. How to fill the electron? These are the orbits. This is the nucleus. Okay. In this nucleus, what is present? Proton and neutron. This is the nucleus, and these are all the orbits. K, L, M, N. These are the orbits. Orbit K shell, L shell, M shell, N shell. Then K shell is the first one, second one, third one, fourth one. These are all the shells. Clear? How the electrons are filled? So it should be start with the 1s. It's arrow marks. You see clearly. This chart is given by one of the side is called molars. Okay, molars diagram. Okay, it is otherwise said to be as a chemical tool for calculating the electronic configuration. If you know this one, you can do the electronic configuration very easy. Very easy, you can do it. Clear? So see, the electrons should be filled like this. First you have to fill 1s. When the 1s is filled here, it should be entered into the 2s. Clear? After 2s, it should enter into 2p. Then 3s. Then after 3s, it enter into 3p. Then 4s. Okay. After 4s, it enter into 3d. Okay. After 3d, then 4p, then 5s. After 5s, enter into 4d, 5p, 6x, and continuous. Clear? This is the way how to fill the electrons. Now see here, 1s, then 2s, then 2p, 3s. After 3p, 4s. After 4s, the 3d is there. Now why like this here? Why we are writing 4s here and why we are writing 3d here then? After 4s, we are writing 3d here. It indicates that 3s, s orbital is very near to the nucleus. So the electrons will fill s orbital first, then it will go to the d. So the 3d, after 4s, the 3d will come. Suppose in your area, okay, in your area, now if you are feeling very hungry and you want to eat the biryani then, so 3 to 4 hotels are there nearby you. Okay, very near, one hotel is there, little bit far, other hotel is there, then still far, one hotel is there. But all the 3 hotels cook the biryani very nice. Okay, very spicy one, good one. So when you are feeling hungry, which hotel will go? You will prefer the near one. Clear? Exactly like that here, the electron prefer the nearest one. So nearest orbital is 3s only, s only. After s, then p, then d, then f. Clear? This is the way the filling the electrons. And here you can see here, orbitals already have shown to you. The shell name, subshell, maximum electrons, how many should be filled? Then shell, maximum electrons. Shell name here K, Subshell is 1s. How many electrons can be filled here? Maximum 2, not more than 2. Okay, total number of electrons are 2. Clear. Now K is there. In this, how many subshells are there? S and P. 2s, 2p. 2 are there here. Then 2 plus 6. P means 3 are there. Clear. 3. P means 3. 1, 2, 3. DJ. 3 degenerate orbitals are there. So 3. 2 plus 6, 8. Now check the M1 here. Now. M have the 3s, 3p, 3d. These are the subshells present in M orbit. Okay, in this M. In this M orbit, how many orbitals are there? 3s, 3p, 3d. Now 3s, S means only 2 electrons only can fill here. P means here not 6, definitely. Then D means here 10. Okay, 10 I have shown you, clear. In one of the topic I have shown you for this field here, 10. Now count it 10, 16, 17, 18. Total number of maximum electrons can be filled in this shell is 18. Last and final N1, outermost orbit. Okay, outermost orbit. This orbit plays a very important role in electronic configuration. Clear? So last one, 4s, 4p, 4d, 4f. S always 2, p always 6, d always 10, and f always 14. Not more than this. So total you see. Okay, 14 plus 6, 20, 30, 32. Total 32. These are the subshells. These are the orbitals. This box is called as the orbitals. Okay, 5 orbitals, 7 orbitals, 3 orbitals, 1 orbital. 1 orbital, 2 electrons. 6 orbital, 2, 2, 2, 6. Okay, like that is a failure. Clear? This chart is nothing but a Mollard's diagram. This chart shows that how the electrons fill up, in what the way the electrons will fill. Clear? Now we'll do the electronic configuration. Clear?